Now let's do some state space modeling of a circuit. So we have our example circuit. This is our standard RLC circuit. And we're going to model it in state space. And we're going to make two outputs. I know, this is crazy. We're going to have two outputs. One of our output, our target, will be this voltage. So it'll be the capacitor voltage. Oops, VC. And the other one will be the voltage over this resistor. So we'll call that, VR. And our input is Valerie. She's controlling our voltage here on the input. So let's model this system. Oh, sorry, this is our second output. So our output 1 and 2. So let's model that. All right, and just to remind you, this is our standard form for state space modeling. If I say put it into state space form, it means you need to find A, B, C, D and write it in this form. And as a reminder, A, B, C, D are all matrices. They might be one-dimensional or 1, 1, 2, 2, but they are matrices, and then X and Y and U are vectors. So where do we start on this? I'll give you my approach for working with circuits. If we remember the equation for an inductor, we have for a capacitor, oh gosh, I always fail this one. It's V equals L dI equals L di dt, and I is equal to C dV dt. Okay, and here we're defining the current the same through all of them, and then each of these voltages. So these are our equations, and we have this derivative here. We want to find a derivative equation for each of these, so it makes sense that we name our states to be VC here and I. So you get to choose which states, but you have to make sure you're capturing all of the dynamics in the system. So in this case, we're going to define, we'll say X1 is equal to this capacitor voltage, so VC, and we're going to call X2 I. Okay, and remember our outputs, so let's just write them here now. So we're going to have Y1, that's going to be VC, and our Y2, what is that going to be? That is going to be, well, the current times R, so it's going to be RI. And if we change these into our state space, VC is just X1, and RI would be RX2. Okay, so we've got all our main definitions, and we can do some things here. And so these so far are all in our states, so VCI and VC and I, but we have this VL as well. So we actually need to find a new equation for VL. But if we look at the summing up all of these voltages, so if you do KVL, we know this is the, oops, that's an L. We know that this voltage has to be equal to the sum of these voltages. So let's write that down. We have V, and I'm going to drop the of T's here again. So V, our input, is equal to IR, right? Plus, well, VL, let's put it this way, and then plus VC. Okay, so if we put these together, we can actually get rid of our VL. So let's substitute this into here. So we'll get V equals IR. Substitute this in, plus L di dt, oops, plus VC. Now we want to get di dt all alone, so let's move things around and then divide. So I'm going to move this over here, I dt, and we will get, so it would be 1 over L V minus R over L I minus 1 over L VC. Believe that's right. Okay, so now we have the dynamics written here. And we already know this equation, right? So dvc dt is equal to 1 over ci. Okay, so now let's transform some of these. Instead of going in our I and V and all that notation, let's put x1, x2 first. We forgot to write something down. We also need to know the input. So our input, U1, is equal to V. Valerie's controlling our input at the voltage, so that's V. Okay, so now we have everything defined, and now we can replace these two equations with our state space. So let's do that. Okay, so let's have x2 dot is equal to 1 over L. V here is our input, right? So U minus R over L. I is x2, so x2 here. Minus 1 over L. VC is x1. Oh, right here. VC is x1. Okay, and we'll do the same thing with this one. x1 because VC is x1. And we have 1 over C, and I is x2. Okay, so looking at this, we can now put this into our matrix form over here. So let's move it up over here. But we'll do x1 dot, x2 dot. Now we have to figure out our A matrix. And we can kind of look at this one and see only relies on x2. So we'll have a 0, 1 over C. And now we're going to fill in this part of the matrix. So we're going to have a negative 1 over L, and then a negative R over L, times our states x1 and x2 here. And now we have to look at inputs. x1 does not depend on U. Put a 0 here. Next to we have 1 over L times U. Great, so again, here's our A, and here's our B. Now, what about Y? And we have 2 now. What do we do with that? Well, we have already kind of written it here, so let's see what we can do. So we're going to put Y1, Y2, and it's going to be equal to, we have to see how Y1 and 2 depend on X1 and X2. So we're going to make a matrix here. So we have 2 states and 2 outputs, so it's going to be a 2 by 2 matrix here. X1, X2. Okay, and our Y1 only depends on X1, so we have 1 and a 0 here. Our Y2 depends only on X2 and is multiplied by R, so we have R here and a 0 here. And then they don't depend on U, but we should just be proper and write down D here. So 0 times U. So this would be the state space modeling of our RLC system here. And this, again, is C and D. So now we've fully modeled it in state space, and we could go forward with doing some analysis on it. But for now, we're just modeling, so this would be the final form.